Hello everyone, welcome to some Flowers Mathematics and Physical Science YouTube channel, and today we're looking at momentum and impulse from physical science grade 12 in paper 1. So we'll be looking at 3 questions. Question 1, multiple choice, and question 2, just questions on momentum and impulse, and also question 3, questions on momentum and impulse. I'm going to start off with question 1, which is MCQ. Now it says here, football, which is kicked horizontally, hits the goal post and bounces back horizontally, with the vectors P initial going to the right and P final going to the left, as shown below, which represent the linear momentum of the ball before and after the ball hits the goalpost. Now, which one of the following vectors represent the change in linear momentum, change in P of the ball? A shorter left, or B, a longer left vector, and C, a longer right vector, and D, a shorter right vector. Now let's break it down. We have P initial going to the right, which is a longer right vector, and we want to get our change in P. And there is no greater explanation that I can put than to say, to give an example scenario of what the change in momentum would be like. So the vector for change in momentum, if we were to take this as a push forward force, that equates to, I don't know, we can give it a figure and say 100%. So this is 100%, and then P final would be 60%, as we check how the vectors are comparing. Now, the impact that the ball hits the goalpost will be felt by the momentum that was initially given. Why? Because this one is short of 40%. And how do you complete that 40%? That's the 40% it fills. Basically, I would put it in a way like in Newton 3, that two people are scrumming together. Well, not two people, let's say two teams, South Africa versus New Zealand. The New Zealand side's momentum is the 60%, and the South African side is the 100%. The New Zealand side is going to feel 40% of the South African side and lose the scrum, and therefore the change in momentum that they feel will be going towards them. I think that summarizes it in the right way if you are a big fan of rugby. Right. Now, in question 1.2, a body moving at a constant velocity has momentum P and kinetic energy E. The velocity of the body is doubled. Which one of the following correctly gives the magnitudes of both momentum and kinetic energy? Well, you have momentum and kinetic energy. A says momentum stays the same, kinetic energy changes. B says stays the constant, and kinetic energy stays constant. C says both of them changes. D says momentum changes and kinetic energy stays constant. Remember, the only thing that has changed here is that the velocity of the body is doubled. So let's put it into terms. In 1.2, we have our velocity being 2v now. So which means our new momentum will be given by mass times velocity, which is mass times 2v. Therefore, this is 2 times the momentum because it's 2mv. So it changes. Then let's check our kinetic energy. E is half mv squared. Now you double the velocity, you're gonna get a half m times 4v squared. 4v squared. Right. Then this will be equal to half times 4 is a 2mv squared. Remember that E is half mv squared. Now how many half mv squared are in 2mv squared? That's about 4. So this is 4e. Basically, you would quadruple the kinetic energy and double the momentum. Okay. So to go back to the question or the table in question 1, the correct answer would be to say both of them change. Momentum will change and kinetic energy will change. So, in a nutshell, I'll just summarize this to say in 1.1, the answer would be D. And in 1.2, the answer would be C. Right. Question 2. I think I'll have to bring question 2 closer so we can quickly observe without scrolling. Right, question 2. A car of mass 1085 kilogram traveling in the eastward direction at a speed of 33 meters per second collides head on with an ambulance vehicle of mass 3450 traveling in the westwards at a speed of 28 meters per second as indicated in the diagram. Alright, immediately after the collision, the car moves west at the speed of 5 meters per second. Then you ignore frictions and other rational effects. Question 2.1 wants you to state the principle of conservation of linear momentum in words. 2.2.1 was the velocity of the ambulance vehicle after the collision, and 2.2.2 was the magnitude of the impulse on the ambulance vehicle during the collision. And then 2.3, they ask or they state that the traffic officer at the collision scene makes a statement that the driver of the car sustains minor injuries because he was wearing a seatbelt. Then we'll have to use relevant laws of physics to explain why the traffic officer's statement is valid. Okay, I think I'll have to attach question 2 here so that we don't scroll too much. Question 2. There you are. Right. State the principle of conservation of linear momentum in words. Question 2. 2.1. Principle of conservation of momentum in words states that the total linear momentum in an isolated system is conserved in magnitude and direction. Okay. Question 2.2.1. Calculate the velocity of the ambulance after the collision. All right, we'll have to jot down the before and the after in our what I call toolbox. But before that, we have to choose direction and its signs. So 2.2.1 is basically the application of the principle of conservation of momentum. Right. We will choose our eastwards direction to be a positive, such that before the collision, the car with a mass of 1085, sorry, will have, or which has a velocity of 33 meters per second and ambulance with a mass of the ambulance speed 3,450 kilograms and having a velocity of 28 meters per second. That is going in the opposite direction, which is westwards, so it's a negative. Let's go back to our scenario here. So we see, all right, then afterwards, the only thing that changed here is that the car moves with a speed of 5 and it's moving now west. So after, the car's velocity is now minus 5 meters per second. Then the ambulance velocity is unknown. So I will denote this as mass of car, velocity of car before or initial velocity of ambulance, initial velocity of ambulance, finally velocity of car, finally, and mass of ambulance. So the masses remain the same, they don't change in this case. Right, let's see how we calculate the principle of linear the principle of conservation of linear momentum. It says that the total sum of the momentum before will be equal to the total sum of the momentum after. This means that P initial of the car plus P initial of the ambulance will be equal to P initial of P final or P after of the car plus P final of the ambulance. So mass of the car times velocity of the car initially plus mass of the ambulance times mass of the ambulance initially. Not mass, velocity. Sorry about that. Velocity of the ambulance initially will be equal to mass of the car times velocity of the car finally or after the collision plus mass of ambulance multiplied by velocity of the ambulance finally, which is what we're looking for. And then we do plugging and playing of our data. Right, we have the mass of the car being 1085, which is multiplied by velocity of the car, which is 33, plus mass of the ambulance, which is 3450, multiplied by a negative 28, because that's before it was going westwards. Then the mass of the car is still remaining at 1085, multiplied by negative 5, plus 3450, multiplied by VF. Okay, and when we do the summation here in the calculator, we get the sum of minus 60,795 is equal to minus 5,425 plus 3,450 V final. And when we take negative 5,425 to the left, it changes sign so that it becomes a plus 5,425, which is equals to 3450 VF. Do we call it VF or VAF? V of ambulance, final, V of ambulance, final, V of ambulance, final. Right. Let us divide on both sides by 3450, 3450, and then our V of ambulance, finally or after, will be equal to a minus 16.05 watt meters per second. Okay. And when it says minus, this means it's going to the west. So it's 16.05 meters per second west. Okay. Right. Next question is asking us the magnitude of the impulse on the ambulance vehicle during the collision. Magnitude of the impulse on the ambulance. Now it's on the ambulance. 2.2.2 impulse. What is impulse? Impulse is product of the net force and the time. Which is equal to change in momentum, which is equals to mass velocity minus velocity final minus velocity initial. And then this is on ambulance. Mass of ambulance is 3,450 kilograms. V initial of ambulance is, we're still taking our eastwards to be positive, so this direction is positive, therefore it was going at a minus 28 meters per second, and finally it was going at a minus 16.05 meters per second. Then if we substitute, we're gonna get 3450 multiplied by negative 16.05 minus negative 28, and we close down, we get a 41,227.5 Newton per second. We're getting a positive value, so that is the impulse on the ambulance from the car. Which is going eastwards. Two point three is asking us, states that the traffic officer made a statement that the driver did not sustain major injuries but sustained minor injuries because he was wearing a seatbelt. Now we must use the laws of physics to explain how did that happen. The laws of physics say that which laws of physics back us up? If we look at Newton's second law of momentum, it states that what F net is equals to change in P over change in time. Right. With F net equals to change in P over change in time, as you put on a safety belt, your body is one with the vehicle, so you have inertia. According to Newton 1, the inertia enables you to resist any force or any movement as the car is moving. So the car crashes, then the seatbelt holds you to not move with the same speed as the car was traveling with. Therefore, this increases collision time. It increases collision time. And when it increases collision time, it decreases the net force. Why? Because if we can check, F net is inversely proportional to time. So when time increases, the net force decreases. When time decreases, the net force increases. So the person will feel a less or decreased net force from the collision because they have got a seatbelt on. Okay. I want to do the last question number 3, as quickly as possible because I think This question has taken a bit long. Alright. A 300-gram ball is dropped from a certain height above the ground and strikes a rough surface, wooden block. And the ball exerts an average net force of 60 newtons during the contact time of 0.5 seconds with the block at point A. Then the ball rolls from point A to point C. Now, 3.1 state Newton's second law of motion in terms of momentum in words. Right. Three point one. The law states what? The net force acting on an object the net force acting on an object equals to the rate of change of momentum in the direction of the net force. Okay. 3.2 is the collision between the ball and the block, elastic or inelastic. So a collision is elastic when objects collide, they move away from each other, and a collision is inelastic when objects collide and they stick together. And in this case, the ball and block collide and then they stay in contact because the ball rolls on the block, so they are in contact, they're not attached together, so therefore it's inelastic. I'm gonna have to say 3.2 and type it down. Inelastic. Okay. In 3.3, they are asking us of what? Calculate the momentum of the ball at the instant it strikes the ball or the block at point A. And you are given mass from the statement. You're given average net force, a given contact time, and you want the velocity that it hits point A as it was dropped. Now, let's have this short scenario here. The ball is dropped. So if it's dropped, its velocity is 0 that it's dropped with. But the one that it hits the ground with, we don't know. So that's what we are looking for. And we take downwards to be a positive. Now if downwards is positive, this means from F net, which is the average force, F net with that contact time, which is delta t, is equal to the change in momentum, P. We have what? 60 newtons and a contact time of 0.5, which is equal to the mass, final velocity, initial velocity. Now this is 30, which is equal to our mass, which is 300 grams, and 300 grams is the same as 0.3 kilograms. So 0.3 kilograms multiplied by the final velocity, which we're looking for, minus the initial, which is 0. Then we divide both sides by 0.3. Then we get that our V final will be equal to 100 meters per second. Where is it going? It was going down. The one that it hits the ball with. Okay, now the question did not ask us to calculate velocity. It said calculate momentum of the ball at the instant it strikes the block. So P is equals to M times V. The mass 0.3 multiplied by 100 meters per second. Then you get 30 kilograms meters per second going downwards because it's a positive. So take positive as we take downwards as positive. Right. Then let's move on to 3.4, which I think I have a picture of it. Right. 3.4, the momentum time graph for the motion of the ball from the instant it strikes the block from point A to C is shown below. 3.4.1, write down the quantity represented by the gradient of the graph. So we have a graph where looks like this, and then this is momentum, and then this is time, and then it looks something like this. And we are asked about the gradient. The gradient says change in y over change in x. Or change in y is change in momentum. Change in x is change in time. And what do we know that is change in momentum over change in time? It's F net. Therefore, our answer for 3.4.1 is a net force. Okay, 3.4.2. calculate the magnitude of the net force or net average force exerted by the ball on the floor from point B to C. At point B, these are the things to note. And point C, right. We have momentum initial at point B, which is 45. We have momentum final at point C, which is 80. We have time initial. Point B is 30. Time final, point C, which is 40. Then we must get the change in time, which is 40 minus 30, and that's 10 seconds. Also, we must get change in momentum, which is 80 minus 45. Now, a formula that combines these three, there's two of them, impulse momentum theorem, or F net is equal to delta P over delta T. So we'll go with F net is equal to delta P over delta T. Now, this is just P final minus P initial over delta T. And we have found that this is equal to 35 over 10, which is equal to 3.5 newtons. Right. May I please apologize for the small technicalities that we have with our stylus pen and my crazy voice because of the morning sinus flu. Please like, subscribe, and share this to the relevant learners and teachers who will be using this video. Thank you.